This is the video for section 8.2 notes, slides 19 through 22. All right, so in this part, we're actually still doing volumes by rotation. We're still creating objects in the same way, but now we have a different strategy for how we're going to find the volume. All right, so this is called the cylindrical shell method. All right, so we're going to kind of talk about the method, and then you can write down this other stuff. All right, so let's say that we have a graph that looks something like this, right? So we're actually going to use the function that we're going to use on the next slide. So y equals 4x minus x squared. All right, so this is y equals 4x minus x squared. All right, and then the horizontal line y equals 0, right? So we have this region that we're creating. All right, now if we want to revolve this around the y-axis, all right, the key here is that if we're going around this vertical line, right, using the washer method, we would have to use a dy, right? And that is problematic because then we would have to solve this for x. So in order to solve this for x, we would actually have to complete the square, and that's kind of annoying. So what if we could use a parallel rectangle? All right, so let's say that we could use a dx. Now this is parallel, right? And so using the cylindrical shell method, the cut is always parallel to what you're revolving around. All right, so now let's think about what object is created when we revolve in this parallel rectangle around the axis of rotation. All right, and so what we do, and this is kind of hard to draw, so I'll show you an animation of this again. All right, but basically when we revolve this, we're going to get something like this. Now that's just the top edge. So imagine we revolve the bottom edge as well, right? And remember, these are connected, right? So what we get is what we call a cylindrical shell. All right, so let's look at an animation of this. All right, so let's go over here. All right, and I'm going to use this, right? So let's say we have this. All right, so we, divide this up, right? Now we're going to pick one of them, all right, to be the dx that we're using, right? So imagine this dx here, right? Now we revolve that around the y-axis, all right? So now what we have created is what we call a cylindrical shell. So it's a cylinder, but it's like hollow and it doesn't have a top or bottom, right? Okay, so that's what we're dealing with. So we have a cylindrical shell. So imagine that we did a bunch of those, right? Then we would have one of them revolved, and another one revolved, and another one revolved, and so on. All of these put together are going to create this whole three-dimensional object, right? Now remember, if those shells are infinitely thin, then they're going to create this three-dimensional object. So this one, I don't know, kind of looks like a bundt cake or something like that, all right? But the key is that we understand the single shape that is created, right? So what we get is what we call a cylindrical shell, all right? So now we want to think about this, all right? So first of all, this is something that, like imagine this was like a piece of paper, right? And so if we had this piece of paper kind of rolled up, what would happen if we unrolled it, right? So I always look at this as kind of like the label on a can of soup or something like that, right? So if we peel this label off and lay it flat, we actually just get a rectangle, right? Now, the rectangle is something that has a height that is the length of the dx, right? So the length of the dx. So this is the dx rectangle's height, all right? So how would we find the height of the dx? We would take the upper boundary minus the lower boundary. So you can write yourself a little note there. Upper boundary minus the lower boundary. All right. Now, what about the width? Well, remember, this is like the soup label, right? The label on the can of soup. So if you unroll this, what is this width of this rectangle? Well, it's actually the circumference of the circle, right? So how do we find circumference of a circle? Well, remember, c is equal to what? 2 pi times the radius, right? Now, what's the radius? All right, so let's go over to this picture here. The radius is represented by the distance that the dx is from the axis of rotation, all right? So this is something that, people kind of struggle with. So we're talking about this distance here, right? So how far is that distance? Well, remember, dx changes, right? Because there could be a dx here or a dx here or whatever. So dx is actually just x units from the y-axis. Now, the y-axis happens to be the axis of rotation here, and so we would say that that distance is just x. Now, let's say that we weren't going around the y-axis. Let's say we were going around, like, I don't know, x equals -1. Then how far is the dx from there? We would say x minus -1, right? So that is the radius of this cylindrical shell. So that's what's going to go in there. All right, so the distance from the axis of rotation. Okay, and so now, how would we find the area, two-dimensionally speaking, of this cylindrical shell, right? We would take the height, so that's the height, the upper boundary minus the lower boundary, multiplied by the circumference, 2 pi r, right? All right, and so we come up here, right? Then we're going to apply a thickness to it, right? So the area, two-dimensionally speaking, is 2 pi r h, right? And then how do we transition it to be a volume? Well, we take the area, 2 pi r h, multiplied by its thickness. Now, what's the thickness? Well, it's the dx, the infinitely thin thickness of this cylindrical shell, all right, or of this dx rectangle, all right? And so now what are we going to do? We're going to add up all of the infinite number of these cylindrical shells. All right, so just a reminder, r of x, right, that's a function of x, right? H of x, that's a function of x. 2 pi, that is a constant, so we can put that out front. So 2 pi r h, and then times the thickness dx. From a to b, remember, if we're integrating with respect to x, that's from left to right, and if we're integrating with respect to y, that's from the lowest value to the highest value. All right, so now let's actually do this problem on slide 7. All right, so y equals 4x minus x squared, right? And y equals 0, so that's the region that we described. All right, and we are revolving around the y-axis, right? So here's the y-axis. All right, so now, using the shell method, remember, we're using a rectangle that is parallel to the axis of rotation. All right, so dx is parallel to the axis of rotation. So we're going to start off, we're going to say 2 pi times the integral of radius times height with respect to x, right? So this is how I'm going to start off every shell method question. All right, so if I recognize a shell method, then I'm going to start it off like this. Remember, shell method means the rectangle, the dx or the dy, is parallel to the axis of rotation. All right, so I have a dx and it is parallel, so shell method. All right, so now we put 2 pi radius times height. All right, so radius, what's the radius? Remember, the distance that a dx is from the axis of rotation. Remember, the dx is x units from the y-axis, and the y-axis is 0, so we would say like x minus 0, right? All right, height, upper boundary minus lower boundary. What's the upper boundary? All right, upper boundary is 4x minus x squared minus the lower boundary, which is y equals 0. All right, and now we're going to integrate from what to what? Well, from left, which is 0, to right, which is 4, right? So this would be the volume that we would be generated by revolving that region around the y-axis. All right, now this would be one that obviously would be easy enough to carry out, but we would simplify a little bit. 2 pi times the integral from 0 to 4 of x times 4x minus x squared dx, of course, right? And then we would distribute the x. So 2 pi times integral from 0 to 4 of 4x squared minus x cubed with respect to x, all right? And so then we could carry it out pretty easily, right? So 2 pi times 4x squared, so that would be 4x cubed over 3 minus x to the 4th over 4, and evaluate from 0 to 4, right? All right, so 2 pi times 4x cubed, so 4 times 4 cubed over 3 minus 4 to the 4th over 4, right? And then minus 2 pi times, well, this would be 4 times 0 cubed over 3 minus 0 to the 4th over 4, right? Okay, so then, of course, we would be able to finish that off. And yes, the numbers could get a little annoying, but remember, the point is that this is something that we can do by hand, right? So 4 times 4 cubed. 4 cubed is 4 times 4 times 4, which is 64, times another 4 is 256 thirds minus, now this would reduce, so this would just be 64, right? And then minus 0, and then don't forget about the 2 pi, right? So 256 thirds minus 64, of course, then we would multiply 64 by 3 over 3, so we would get 256 thirds minus 64 times 3 is 192 thirds, so 256 minus 192 gives us 64 thirds, right? But then we're multiplying by 2 pi. So we would get 128 pi over 3, right? So that's one. Yes, I know these numbers, a little bit big, but really not that big of a deal, all right? So that is the cylindrical shell method, all right? So let's go ahead, slide 21. All right, so same thing. Now we're just going to set these up, all right? So it says, find the volume of the solid generated when the region bounded by y equals x minus 2 squared, right, which is the parabola shifted 2 units to the right, y equals 0, x equals 0, and is revolved about the x-axis. All right, so first of all, what is the region? Well, I have this graph here, this parabola shifted 2 units to the right, y equals 0, remember, horizontal line, x equals 0, vertical line, so this is the region that I am interested in. All right, so the first part says let's use the shell method. All right, and revolved around the x-axis. All right, so revolved about the x-axis. All right, so shell method would require, I'm actually going to use blue here. All right, so shell method would require that I have a rectangle that is parallel to the axis of rotation, right? So I'm going to use a dy. So use dy, okay, because it's parallel to the axis of rotation, all right? Which means when I'm going to do part B, right, we'll use a different color there, I'm going to have a rectangle that is perpendicular, so that's going to be a dx. So write yourself a note there, use dx, all right? So let's go ahead and do the shell method first. All right, so shell method says 2 pi times the integral of radius times height with respect to y, all right? Disk method, okay? Disk method would be pi times the integral of radius squared with respect to x, right? Now, why is it the disk method and not the washer method? Well, because remember, this region here has no gap from the axis of rotation, so it would be the disk method, all right? All right, so let's go back to the shell method. All right, part A, all right? So shell method here, remember, if I'm going to use dy, that means I need my equation to be in x equals form. So I'm actually going to have to solve this for x. All right, so y equals x minus 2 squared. All right, so first of all, I'm going to square root. All right, so when I square root, I get plus or minus the square root of y equals x minus 2. So x is equal to 2 plus or minus the square root of y. All right, so plus or minus. Remember, plus or minus splits the parabola into 2 halves, the right half and the left half. So which one do we want? We actually want the left half, don't we? Because that's going this way, all right? If you're unsure, you could always, pick a number, plug it in, and make sure that you actually want that. So let's say I wanted to get the y-intercept, right? That is found by plugging 0 in for x, right? So if I did that, I would get 0 equals 2 plus or minus the square root of y. Well, how are you going to get 0? Only if it's 2 minus the square root of 4, right? All right, so we want x equals 2 minus root y. All right, so now, shell method. All right, radius. So remember, this is 2 pi radius times height. All right, so radius. Remember, the radius is the distance that the dy is from the axis of rotation. Remember, the dy is y units from the x-axis. The dx is x units from the y-axis. All right, so y is the radius, right? Y minus 0, right? Because 0 is the axis of rotation. All right, height. Now we're taking the upper boundary, in this case, the right-hand boundary of the dy, which is 2 minus root y, minus the left-hand boundary, which is 0. All right, now, of course, you don't have to have the minus zeros, all right? But now, integral from what to what? The lowest y value is 0 to the highest y value is 4. All right, so you could simplify that a little bit just by dropping the zeros, right? So now that would be the volume of the object created by revolving this region around the x-axis. All right, now let's do it with the disk method. All right, so disk method uses a dx. All right, so now pi times the radius squared. All right, radius, remember, radius in the disk method is just upper boundary minus lower boundary. All right, what is the upper boundary? It's the curve, but remember, we need to be in y equals form. So the curve is x minus 2, quantity squared, minus the lower boundary, which is 0. So, of course, you could drop the minus 0, and you would have x minus 2 squared, which would actually be x minus 2 to the 4th. All right, now we're integrating from what to what? Well, from left to right. So what is the furthest left this region goes? That's x equals 0. So the furthest right this region goes, that's x equals 2. And so now, this is two different methods of finding the same value. So if you were to carry out these, you would get the exact same value. So a nice quick check would be to actually plug these into your calculator and make sure that they do indeed get the same value. All right, so that is slide number 21. All right, so let's go on to slide 22. All right, so slide 22. Find the volume of the solid generated when the region bounded by y equals x squared plus 1, y equals 1/2 x equals 0, x equals 6 is revolved about the y-axis. All right, so you should be able to draw this graph. All right, y equals x squared plus 1, basic parabola shifted up 1, y equals 1/2 x, line with a slope of 1/2, y-intercept of 0, x equals 0, vertical line, x equals 6, vertical line, right? So we get this picture, all right? Now, I'm revolving about the y-axis. All right, so now, here's the question. It doesn't say to use the shell method or the washer method. Some of our problems will, but in general, the AP is not going to tell us use the shell method, use the washer method. It's just going to say find the volume. And so we have to make sure we are mindful of, well, what should we use? Should we use the shell method or the washer method? Well, we don't actually say, I want to use the shell method or I want to use the washer method most of the time. We're actually going to say, what's going to be easiest to use, a dx or a dy? So now, I'm going to zoom in on the picture a little bit. All right? All right, so now, let's think about dx or dy. All right? So if I draw a dx here, okay, and I move it anywhere in the region, right? Upper boundary is always that curve. Lower boundary is always the line, even all the way over here, right? So it looks like a dx is going to be better, right? But let's say I go back and I say, okay, well, what about a dy? Could we use a dy? Well, if I used a dy here, that would be fine, okay? This right-hand boundary, left-hand boundary. But then I get down here, and the right-hand boundary would be the line, and the left-hand boundary would be that curve. Everyone see that? And then I go even further down. It's really hard to see, but at a certain point, the right-hand boundary would be the line, and the left-hand boundary would be the y-axis. And so that would mean I would actually need 3 separate integrals, which is probably pretty annoying, and so we actually don't want to do that, right? We want to use 1 integral as opposed to 3, right? Now, there's a little bit of extra motivation for this as well. All right, so let me show you the extra motivation. All right, the equations that you are given are in y equals form. So what does that mean? Well, you're not going to have to do any extra work to get them into x equals form if you wanted to use a dy. All right, so we always look at the region first, okay? We decide whether or not a dx or a dy is easier to use, right? Sometimes the way that the equations are written might dictate that as well. All right, so we're going to use a dx, which is parallel to the axis of rotation. So that means we're going to be using the shell method, right? So use shells and dx, right? This is what we've decided based on how much easier it would be to use this method, okay? All right, so now I set up 2 pi times integral of radius times height with respect to x. All right, so radius, how far is this from the axis of rotation, right? So it's x minus, well, whatever the axis of rotation is, 0. Now remember, let's say we weren't going around the y-axis. Let's say we were going around like x equals -2, right? This would be x minus -2. All right, what if we were going around like x equals 8? What would we do? We would put 8 minus x. Why 8 minus x? Because 8 is over on the right side. 8 is greater. We're trying to figure out this distance, right? This distance is x. This distance would be 8 minus x, right? So just keep that in mind as we're going through some later problems. But anyway, this one is going around the y-axis, so it's x minus 0. All right, times the height. All right, height, remember, is just the upper boundary minus the lower boundary. All right, what is the upper boundary of the dx? It's the x squared plus 1 minus the lower boundary, which is the 1/2 x. All right, so I have 2 pi times the radius times the height, and then integrating from what to what? So left to right. So furthest left is 0, furthest right is 6. All right, and so this would be the volume generated when this region is revolved about the y-axis. All right, so now of course you could carry this one out, right? You'd have to like get rid of the 0, you distribute the x, right? But we're going to focus primarily on setup. All right, so that is slide number 22.